We're going now to consider edges that have directions. This way we will extend the definition of graphs to directed graphs. In previous applications of graphs, an edge was used to represent a two-way or symmetric relationship between two vertices. Now, there are some situations where the relationships hold in only one direction. A directed line segment is used. So here's the definition of directed graph. It's very similar to the regular graph definition. A non-empty finite set V, the set of vertices, and a set E, which is the set of edges. Now in this case, each edge is considered to be an ordered pair of elements of V, the set of vertices. Here's one note. In a graph, we don't allow directed loops, directed edge from a vertex to itself. And we don't allow parallel directed edges, which is more than one directed edge from one vertex to another. Let's take a look at some examples. So here is an example of a directed graph. The set of vertices is very similar. You list the vertices, and the edges are made of vertices, but as an ordered pair, a set of ordered pairs. So for example, here we see two ordered pairs, AB and BA. These two are different. This represents a directed edge from A to B, an edge going from A to B. And this represents an edge going from B to A. So here's a diagram. Because we consider directed edges, we use arrows to indicate that. So here is the edge AB, A to B, and then also the edge from edge B to A. Notice that there are no edges C to B. There's one edge from B to C. So this is very important. And the edge C to D. So there are four different edges, even though these two edges here may look the same if we ignore the arrows, but they are different edges because they have different directions. Another observation is that these two are not considered to be parallel directed edges. Parallel edges would be two edges going from the same starting point to the same end point. And here's the adjacency matrix. Notice that the adjacency matrix of a directed graph is not symmetric necessarily. If you look here, each row represents a vertex. Each column also represents a vertex. And this entry here, number 1, represents the edge from A to B. And this one represents the edge from B to A. Notice that this edge here is an edge from B to C, which is right here, but there is no edges from C to B, which is indicated by this number 0. Now we can also talk about directed multigraphs. This is the extension of the definition of multigraphs. In directed multigraphs, we allow directed loops and parallel directed edges. We can also talk about degrees of a vertex, but here we have two different types of degrees. Because we're using directed edges, we can talk about the in degrees and out degrees. In degrees is the number of edges to vertex A. In degree of A is number of edges, directed edges to vertex A. And out degree of A is the number of directed edges from vertex A. Strongly connected multigraph. It means that there is a directed path between every pair of vertices. So you should be able to travel from one vertex to any other vertex through a directed path. Let's take a look at this example, and here we can um, find cycles, we can find paths, but they're all directed. I'm going to omit the word directed because everything we talk now will be directed. Directed simply means that the edges now have directions. If you see here, this is a path from A to B. So we start at A, go through edge A, so going this way. Edge A is a loop, a directed loop. Then we arrive at A again. Now we continue through C, edge C, which is this one. Notice that we cannot have a path going from A through D and arriving at C, because D is a directed edge that would go against the path, will go the opposite direction. So we cannot have that. A directed path can only have edges that go through the same direction of the path. And this path is not a simple path because we repeat edges. So it's the same definition. We're using the same ideas from the regular definition of graphs. A itself, a vertex itself, is a path of length 0. Here is in degree of C, which is 3. And the reason that it's 3, it's because there are 3 arrowheads arriving at C, as you can visualize here. And there are 2 edges going from vertex C, which is D and B. So the out degree is 2. Here is a cycle starting at A, going through C, then B, then edge E, arriving at C, going through D, and arriving at A. So this is a cycle. It's a path where the first vertex is the same as the last vertex. Remember that a cycle, we cannot repeat vertices. Only the first and the last one you repeat. Here's an example of a path that is not a cycle, even though the first vertex is the same as the last vertex, but it's not a cycle because vertex B, for example, here is repeated twice. In other words, we start from C and we go around and we passes through B twice, and that is not a cycle. It's a path with the same starting and ending at the same place, but it's not a cycle. We can also extend the definition of tree into rooted trees. A rooted tree is a directed graph satisfying these 2 conditions. First, the rooted tree is a tree if you ignore the directions, if you ignore the directions of the edges. And if you remember the definition of a tree, it's a graph that is connected and has no cycles. That's the first condition. When you ignore the directions, then the resulting graph is a tree. Now there is a second condition. The in degree of any vertex is 1, except one vertex. That special vertex is called a root, where the in degree is 0. Here's an example of a rooted tree. If you ignore the arrows, replace the arrows with just a simple edge, a simple segment, then what you have is a tree. It's connected. There are no cycles. And then condition number 2, let's put back the arrows there in the graph. The in degree of any vertex is 1. and except one vertex. If you look at each vertex here, the in degree is 1 because there's one arrowhead coming towards C. Here is a vertex F. In degree is 1. In degree is 1 here for E. In degree is 1 for G. But look at vertex A. The in degree is 0. And that's the only vertex that has in degree equals to 0. So this is a rooted tree. You can also draw the diagram where no arrows are needed. In this case, the directions are downward. So for example here, a vertex A and vertex B, there's an edge here. Because vertex A is above vertex B, that means the direction is from A to B, so you go downward. If we assume this, then we don't need the arrows. In this format, you're able to see clearly that A is a root. If you look at the graph here, you can go from A to any other vertex, so A is the root. And here are some results about rooted trees. First, the number of vertices is one more than the number of directed edges. And this is very similar to the result that we studied when in previous chapters. There are no directed cycles in a rooted tree. There is no directed cycles. And also, in a rooted tree, there is a unique, simple directed path from the root to every other vertex. If you remember, there was a result that said that there is a path between any two vertices of the tree. So you can go from one vertex to any other vertex through a path. For rooted trees is different. The rooted trees, you can only say that a similar fact, but from the root to any other vertex of the tree. We can also use family terms to describe relationship among vertices in a rooted tree. We say that a vertex U is a parent of a vertex V if there is an edge, if there is a directed edge from U to V. And we can say also that V is a child of vertex U. We can also define ancestors of a vertex. Ancestors of V are all the vertices except V itself on the directed path from the root all the way down to vertex V. And V is called a descendant of these vertices. Terminal vertex is a vertex that has no children. An internal vertex is a vertex that has children. So if we go back here, let's take a look at this tree. It's easy to use the family terms when we draw the rooted tree in this format. As you can see, vertices H and E, they're terminal vertices. They don't have any children. Vertex F has two children, vertex H and vertex G. Vertex F is an ancestor of vertex G, and vertex G and E are descendants of vertex F. And of course, all the vertices are descendants of vertex A, which is the root of the tree. Now here's another theorem. We can extract a rooted tree from any connected graph. And this is an algorithm that you already know. It's the depth first search algorithm. When the edges are oriented from the lower label number to the higher, then we obtain a rooted tree. So let's apply the depth first search algorithm on this graph. If you remember, first we begin with the root. If you choose any vertex to be a root, then let's say we choose A, then we label that as 1. And from A, then we look at the adjacent vertices and we pick one. So let's pick alphabetically. We have the choice of B, C, or D, but let's pick B. When you go to B, you're going to label that as 2A. And you keep going. From B, you have the choice of C or D. Let's pick alphabetically. Let's go to C. And we're going to label that as 3B. Now from C, we can't go anywhere. So if you remember the rules of the depth first search algorithm, we go back. We backtrack one vertex and then we try to go from there. So we backtrack to B, and from B now we can go to D, and we label that as 4. And from D there's no other place to go, so we backtrack to B. There's no other place to go. We backtrack to A. There's no place to go, and that's the end of the algorithm. And that creates a rooted tree from the given graph.